So let me summarize. What did we prove? We proved the following. Let A and B be two numbers. Let x0, x1, x2, and so on be an AB recurrent sequence. Then, if a squared plus 4b is non-zero, then every n satisfies xn is gamma lambda to the n plus delta mu to the n, where we set, and now we just copy paste these formulas back into the theorem. This is kind of messy. In many cases, these numbers do simplify, not always as nicely as you wish, but it is an explicit formula, it's just long. On the other hand, if a squared plus 4b is 0, then every n bigger than 0 satisfies this formula xn is. And if you really want to make it true for n equals 0 as well, so for any n and n, you have to agree that n times a to the n minus 1 should be 0 if n is 0, even if this per se would be undefined because of division by 0. So that's an answer. And there is a bunch of examples in the notes. I will just show you a couple. So if we apply this to the Fibonacci sequence, then we get the Binet's formula. We recover it, which should not be surprising. So Fn is gamma lambda n plus delta mu to the n, where lambda is phi and mu is psi. This is what you get if you plug in 1 and 1 for a and b here. This is 1 plus square root of 5 over 2, 1 minus square root of 5 over 2. And lambda at gamma and delta, this one is really a somewhat painful computation, but you can get through it. Gamma is 1 over square root of 5, and delta is minus 1 over square root of 5. If we apply this to the Lucas sequence, then we get ln is phi to the n plus psi to the n, which explains what's the point of the Lucas sequences. It has a nicer Binet formula than Fibonacci. Here is a third example. As I said, there is more in the notes. Previously, we said that two periodic sequences are recurrent. So if you have a sequence that's two periodic, so uv, 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 and so on for two numbers u and v, then, as we have seen above, the sequence is 0, 1 recurrent. So we can get an explicit formula for xn using the above theorem. You will see easily that part A applies because a squared plus 4b in this case is non-zero. It would be 0 squared plus 4 times 1, which is 4. We obtain, so applied to A is 0 and B is 1, we obtain this formula where, and now I'm just plugging 0 and 1 everywhere here. What is this? This is 4, so square root of 4 is 2, 0 plus 2 over 2 is 1. For similar reasons, this is minus 1. And this, well, this is v, this is u, this is minus 1, so plus u, this is over 2. We can simplify it as u plus v over 2. This is 1 times u minus v, again 2. Okay, so it does simplify a lot. In other words, x to the n is u plus v half dot 1 to the n plus u minus v half dot minus 1 to the n. And 1 to the n just disappears, it's just 1. Is this surprising? No, because minus 1 to the n is exactly what gives us this two periodicity. Minus 1 to the n oscillates between 1, minus 1, 1, minus 1, 1, minus 1, and so on. So in every even spot, this will be a 1, and you will get u plus v over 2 plus u minus v over 2, which is u. This is how you get all those u's here in the even positions. And in the odd positions, this power will be a -1, so you will get u plus v over 2 minus u minus v over 2, which gives you all these v's here. So this formula gives us the exact behavior we expected. And as I said, there is more in the notes. In particular, there is a way to give a slightly geometric explanation of this 6 periodicity of this 1 minus 1 recurrent sequence. If you know complex numbers, if you know what complex numbers have to do with regular polygons, you can actually explain the 6 periodicity pretty nicely.